All right, in Chapter 9, Section 5, we want to look at interesting examples of alcohols, ethers, and epoxides. We're going to start with alcohols, and the first one we're going to start with is the simplest alcohol, methanol. Methanol is called wood alcohol because it's produced by taking wood and heating it up at a very high temperature without any oxygen present. And when you do, you'll produce that methanol. Methanol has the downside of being very toxic to humans. Just 15 milliliters, which is about half of an ounce, can cause blindness. And 100 milliliters, which is a little more than 3 ounces, can be fatal. So you definitely don't want to drink methanol. You don't want to consume methanol if at all possible. Propanol, 2-propanol, or isopropanol, as it is typically called, or isopropyl alcohol, as you'll see it listed like at the store, also called rubbing alcohol, is an excellent antiseptic. It's made pretty easily and is widely available. So you can get this relatively cheap for purposes of using it as an antiseptic. It's great for cleaning things. I always have some around the house for cleaning equipment, and I use it with my 3D printing and all kinds of fun projects. All right, ethylene glycol. Ethylene glycol is the main ingredient of antifreeze. It has a very broad temperature range for the liquid. It has a very low freezing point and a very high boiling point, and so that makes it a good heat transfer fluid for engines. You can transfer the heat from a hot engine out to the radiator, or but it will still flow even when it is cold. So ethylene glycol is good stuff for that. The downside is it is fairly toxic. And not so much an issue for humans because we won't drink it or whatever, but it is an issue for pets. So if you ever change, this is just a little public service announcement, if you ever change out your antifreeze at home, make sure that you dispose of the antifreeze. Don't leave it in an open container, because if a pet, a dog or a cat, comes along and drinks it, it can be fatal to them. It can cause kidney damage and ultimately can be fatal to the animals. So make sure that you clean that up properly, dispose of it, put it back into the original container. So if you drain some out, put it into your original container, and you can take it to the store where you purchased it, and they will recycle it. As far as some interesting ethers, there are a lot of ethers that are very interesting. We mentioned one earlier, tetrahydrofuran, THF, is a great solvent used for a lot of different reactions, particularly as we go into our second semester. And we'll see here, we've got some other interesting ethers. These are crown ethers. Now, these are a little bit difficult to make, and therefore they are a little bit expensive, but the amount of these that you use is very small. So it's possible to use these and in very strategic amounts, and you'll be able to do reactions that you might not have been able to do otherwise. Now, what they do, these oxygens are Lewis bases. They have electrons. And then our alkali metals, the group 1 metal ions, are Lewis acids. They can accept electron pairs. And so we will find that there is an ion dipole interaction between the oxygen and the cation. Well, in this case, with potassium, there are 6 of those. And those 6 ion dipole interactions add together to give us a very strong interaction. So potassium is kind of locked up in what's called a host-guest complex, where the potassium is locked up in that crown ether. Now, you can do a similar thing with lithium if you use this smaller one that has 4 ethylene units and 4 oxygen units. This one has 6 and 6. And so that one's called 12 crown 4, and it will complex lithium quite well. Interestingly, there's one in between that's 15 crown 5, and it is very good at complexing sodium. So you have a lot of options for producing these crown ethers and using them with your compounds. Now, as I mentioned, these are expensive, so they're not something just to be put in there because they're cool. They're expensive, and there's a reason why we use them. And that reason is it helps us to do SN2 reactions with ionic compounds. Like here is potassium cyanide. Well, potassium cyanide is an ionic compound. It is not very soluble in organic solvents. And so it would be difficult to do this reaction where you're going to react it with something like, I don't know, like this bromoethane. All right. So what we do is we put the crown ether in there with it, and the crown ether will complex the cation, and it will make it so that the ionic compound is more soluble in nonpolar solvents, like benzene, for example. Or weakly polar solvents. If we didn't want to use benzene, we could use toluene or something. And so there we are able to get it to dissolve in something that is not very polar. In addition to that, because it's complex that cation, it makes the anion unsolvated and makes it very nucleophilic, and it's going to be quite reactive. So we increase solubility and we increase the reactivity of our nucleophile. So great tool to use with SN2 reactions. Now, there are a number of interesting epoxides that we can look at. This first one, eplerenone, it is used as a diuretic, so to decrease the amount of water for people who suffer heart conditions. The tiotropium is used, again, this one is used to decrease the amount of water in people's lungs, particularly helpful for people with COPD. Paraplanone B is a sex pheromone for cockroaches, and then here, this one is an effective anti-cancer agent, so it can be used as a chemotherapy agent. So any number of interesting uses. If you look at all of these compounds and you think, wow, those look like they would be really hard to synthesize. Yes, they would be. So these are not trivial to synthesize, but they are valuable enough for people to synthesize them. All right. So now we want to look at how it is that we prepare alcohols and ethers. We've already seen how to prepare alcohols and ethers using SN2 reactions. So alcohols and ethers can be synthesized by SN2 reactions. Here is an example. If you've got an alkyl halide, like this one. So here we've got bromoethane with hydroxide. We can do the SN2 and we will get the alcohol. In a similar fashion, we can take this alkyl halide plus this alkoxide, do the SN2, and we will get an ether. This is called the Williamson ether synthesis, and is very, very useful for producing ethers. Typically, when we do a Williamson ether synthesis, we'll see that that we can produce unsymmetrical ethers like we saw on the previous page, but and there's often two ways to do it, but one way is usually going to be a preferred pathway. So for example, if our goal is to produce ethyl isopropyl ether, well, we could use ethoxide as our nucleophile and 2-bromopropane, which is a secondary alkyl halide, as our alkyl halide. And yes, we can do an SN2 reaction with that and get this as our product. However, the secondary alkyl halide is a little bit slower of a reaction than is ideal for our SN2 reaction. And it also has the possibility of doing an elimination with that reaction. If, on the other hand, we use the isopropoxide and bromoethane, which is a primary alkyl halide, in that case, we will have a primary alkyl halide which is less sterically hindered, and therefore that's going to be a faster reaction. And we're also much less likely to do the elimination reaction because the elimination reaction would be slower on a primary alkyl halide. So there's all kinds of reasons why you would want to use the less sterically hindered alkyl halide. All right, so for preparation of alkoxides, it turns out that this is pretty easy. We just need a base that is stronger than the alkoxide. So if we want to, for example, produce sodium ethoxide from ethanol, we can do that using something like sodium hydride. All right, so the pKa of this alcohol, this is ethanol, has a pKa of about 16. All right, H2 has a pKa of about 35. That means that this acid is much stronger than that acid. So we can get the equilibrium to lie to the right. So if we just use this very strong base, the sodium hydride, the hydride will come in, deprotonate, and we will get sodium ethoxide plus hydrogen gas. Since one of our products is hydrogen gas, that will just bubble right out of our solution, our reaction mixture, and we will get a very clean sample of sodium ethoxide. So this is an excellent way for preparing alkoxides. Now, there are other bases that we can use. Another one that is used is something like sodium amide, and I will show that to you here in just a few minutes. If you want to form an epoxide from a halohydrin, that is fairly easily done. You need something that is called a halohydrin, where you've got a hydroxy group on an alpha carbon, and on the beta carbon, you have a halogen. So, and then we're going to do an intramolecular version of the Williamson ether synthesis. So here we have our halohydrin, so an OH on one carbon and a halogen on the adjacent carbon. We will deprotonate with a strong base. When we deprotonate that with a strong base, that will give us an alkoxide. And then that alkoxide, even though this is a strained ring that we're forming, we can still do this because this is a pretty strong base, and intramolecular Williamson ether synthesis goes quite well. The molecule is right there, so the kinetics is very fast. And we'll produce this alkoxide. Our halide will be a leaving group. And of course, depending on what the base is, that will tell us what the conjugate acid would be. All right, so we're going to look at number 20 on the in-class assignment. So here is number 20. And so here we want to use the sodium hydride to deprotonate that alcohol. All right, so we saw this a little bit earlier. So there is our alcohol. We would end up getting the alkoxide, so negative, and then sodium would be the counter ion, in case we're interested in the counter ion. And then the hydrogen combines with the other hydrogen to give us hydrogen gas. So that is a very favorable reaction, and that will happen very, very easily. All right, on this one, we've got another alcohol, and instead of sodium hydride, we've got sodium amide. But again, we're going to deprotonate that OH. So let's write that alkoxide. So O minus, we'll have sodium as our counter ion, and then NH2 2 minus plus the hydrogen is going to give us NH3. So that is sodium amide. The pKa of ammonia is about 38. pKa of this is about 35. So this is also a very strong base. All right. You're still left over with that ammonia, but that's usually fairly easy to deal with. All right, on this one, we're going to do two subsequent reactions. One will deprotonate, so we're going to get the alkoxide. That alkoxide is going to be a very good nucleophile, and that nucleophile can react with this alkyl halide. So we're just going to draw the final product. All right, so 1, 2, 3, 4, 5, 6. And then oxygen, and then we're going to have a new bond between oxygen and this carbon, and there's 3 carbons there, so 1, 2, 3. And then here we have a methyl. Now, if you're ever doing this and you're having trouble seeing, what that middle step is, it's okay to sort of jot it down like below. So 1, 2, 3, 4, 5, 6. O minus, right? And then here we have the sodium. And then you can kind of keep track of what the other things are. You would have plus hydrogen and plus sodium bromide as your final product. All right. And now on this one, we're just going to add sodium hydride. Sodium hydride will deprotonate that alcohol and form the alkoxide. And then it is going to form this C6H10O. All right, since this is a halohydrin, our product is going to be an epoxide. So we would get that epoxide. Now, as far as the other stuff that we would get, which we don't always have to write, but we'd get hydrogen, and we would also get sodium bromide as a product. Okay, so there we go. That is that particular set of problems. So now let's go back and look at the next thing, which is general features, some reactions that we can do with alcohols, ethers, and epoxides. We'll start with substitution. In alkyl halides, what makes them so good at doing substitution is that we have a good leaving group. So, for example, if we're trying to do an SN2 reaction on an alkyl halide, no problem. The halides tend to be very good leaving groups. So the halides tend to be very good leaving groups. So those reactions happen very, very easily. However, if you try to take a nucleophile and react it with an alcohol, the hydroxide is a very poor leaving group. Remember, the stronger your leaving group is as a base, the worse it is as a leaving group. Well, hydroxide is a pretty strong leaving group, so you pretty much have no chance of eliminating or of substituting for that. So you're not going to have any of the hydroxide act as a leaving group. So we need to convert that hydroxide into a better leaving group. And the way that we can convert that into a better leaving group is to protonate it. So if we protonate the alcohol, so treat the alcohol with a strong acid, it turns the bad leaving group, which is hydroxide, into a very good leaving group, which is H2O. Neutral compounds tend to be pretty good leaving groups. So if you take something like hydrochloric acid, you treat that alcohol with it, you'll protonate the oxygen, you'll form this H2O plus that's attached to the alkyl group, and then that is a very good leaving group. You do need to have a strong acid here because the pKa of this is about -2. So in order to drive this reaction to the right, we need our acid to be stronger than -2. In other words, we need that number to be less than -2. HCl has a pKa of about -7. And so at -7, we can definitely do that. All right. And that means once we form this H2O plus as a substituent on our alkyl group, it's possible to do both substitutions and or eliminations on the alcohols. So that's a way of getting around the fact that hydroxide is a bad leaving group. Alkoxide, also a bad leaving group. So like the hydroxide, alkoxide is not a good leaving group because alkoxides are strong bases. And so ethers generally don't undergo substitution unless you have an acid added. And I will show you the reaction where we can cleave an ether using an acid like HBr or HI. And we'll do that a little bit later in this chapter. Epoxides also have the same kind of leaving group where they're going to have alkoxides as leaving group, but that leaving group is in a strained three-membered ring. And so that means that even though alkoxides tend to not be that great of a leaving group, you will release some energy when you break open this three-membered ring. So in that case, it is possible to break that carbon-oxygen bond without protonating it first. Now, it's also possible to break it after you protonate it. And once you protonate it, then it's really easy to break. But if you have a strong nucleophile, you can do this reaction. And we're going to talk about that in a later section of this chapter. All right. So we now want to look at dehydrations of alcohols to form alkenes. This is a really useful reaction to do. We're going to start with an alcohol, and the alcohol needs to have a beta hydrogen. So here is a beta hydrogen. And then we can do an elimination reaction. Again, we're going to have to use acid, and I'll show you the acid that we use in a moment. But then we can form this new pi bond between our alpha carbon and our beta carbon, and water will essentially be our leaving group. So we've lost H2O across a carbon-carbon bond to make a new pi bond. All right, so how do we do that? Well, it requires that we use a strong acid. And the two strong acids of choice are going to be sulfuric acid and toluene sulfonic acid. They're both strong acids, but in addition to that, their conjugate bases are not good nucleophiles. So these are very good at what we call being dehydrating acids. So sulfuric acid is really good at removing water from compounds. So we can remove that from the compound, and here we'll get the alkene. Toluene sulfonic acid is very similar. We saw toluene sulfonic acid way back in chapter 2. It is a strong organic acid, has a pKa of -7, and shares a lot of structural similarities to sulfuric acid, and so it is structurally related to sulfuric acid, and it just happens to be quite useful for a number of reactions. And we're going to see this. This toluene sulfonic acid show up in a number of different situations. All right, our rate of dehydration. We will find that the dehydration will increase as the substitution on the alcohol increases. So tertiary alcohols will dehydrate faster than secondary alcohols, which will dehydrate faster than primary alcohols. That said, you can dehydrate all three types of alcohols. It's just that the tertiary goes faster. So the tertiary will go faster. All right, so we want to look at Zaitsev's rule when doing dehydrations. We'll find that Zaitsev's rule does apply. So Zaitsev's rule does apply. If we have an alcohol that has more than one beta carbon with a hydrogen, then we will get regioselectivity that will follow Zaitsev's rule. The more substituted alkene is going to be the major product of the constitutional isomers. And so the example here is that here we've got beta hydrogens on these two methyl groups, and then here on carbon number 3. When we do dehydration, we can eliminate between carbon 2 and 3. That will give us this one, which is a tri-substituted alkene. And we can eliminate between these, which would give us this one, which is a di-substituted alkene. The tri-substituted alkene will be the major product. With the secondary and tertiary alcohols, they dehydrate by the E1 mechanism, so they will form a carbocation. So here is the example. Very first step is that we protonate the alcohol. When we protonate that alcohol, that will give us this. H2O is a good leaving group, and it will leave by heterolysis. We will find that that is going to be the slow step in the reaction. It's an endothermic step with a fairly high activation energy. That will form the carbocation. And then once we form that carbocation, a base, and that base can either be the conjugate base of our acid or some H2O that's floating around, that can deprotonate the carbon, or deprotonate this carbocation intermediate, and that will give us an alkene. When it comes to the usefulness of an E1 dehydration, we're going to find that it's much more useful than the dehydrohalogenation that we saw previously. So the E1 dehydration with secondary and tertiary alcohols gives very clean elimination products without really any byproducts that we might get from an SN1 reaction. That clean reaction occurs because there are no good nucleophiles to react with the intermediate. The only nucleophile that's going to be present is the water that we produced. And if the water that we produced reacts with the nucleophile or with the carbocation, then we're just going to go back to our starting material. So that doesn't really complicate matters. We also don't get any competing SN1 reactions. This makes that E1 dehydration of alcohols much more synthetically useful than the E1 dehydrohalogenation of alkyl halides. When primary alcohols dehydrate by E2, or when they dehydrate, they have to occur by an E2 mechanism. Since primary carbocations are too difficult to form, they're highly unstable, their dehydration is going to occur by an E2 mechanism instead of the E1 mechanism. We'll find that that E2 mechanism, it does work. It's slower than the E1 mechanism, but it does work. So you do have to protonate the OH to make it a good leaving group. But then once you do that, a base comes along. Again, the base can simply be the conjugate base of our sulfuric acid. It comes along, deprotonates, and we will protonate the oxygen, and then we will break the carbon-hydrogen bond at the same time, simultaneously, as we're breaking the carbon-oxygen bond, and then we'll make a new bond between the base and the hydrogen to form sulfuric acid, and we'll also form that pi bond. When it comes to the thermodynamics of dehydration, we'll find that the enthalpy of dehydration is endothermic by a pretty significant amount, 38 kilojoules per mole on average. Here are the numbers for a typical one. Going from having these bonds to these bonds, where we break the carbon-oxygen bond, we break a carbon-hydrogen bond, we form a pi bond, and we form the oxygen-hydrogen bond, we'll see that we end up with plus 38. And since it's endothermic, that means that typically this wouldn't be a favorable reaction to do. However, you'll notice that entropy is on our side, because if we look here, we've got one molecule on the left side and two molecules on the right side. And those two molecules on the right side means that the entropy of this system increases even though it is endothermic. So we can control this reaction by increasing the temperature, and that will help to drive the reaction to the right. We can also use Le Châtelier's principle to help us out. If you recall, Le Châtelier's principle says if you've got a system that's at equilibrium, any changes that occur will be counteracted by the system. So a reaction can be driven to the right by removing some of the product. You can drive reactions to the right by adding reactant or removing product. And in this case, if we remove our product, the alkene, we can drive this reaction to the right. If we look at the strength of the intermolecular forces, this one has hydrogen bonding, so it should have a fairly high boiling point. This one has hydrogen bonding, water, has a fairly high boiling point. But this alkene is going to have a pretty low boiling point because it only has dispersion forces. So because it's less polar, and in fact not very polar at all, this one's completely nonpolar, you can usually just distill this one off, and that will drive the reaction to the right. Okay, so the next thing that we want to look at is we want to look at numbers 46 and 50. All right, so here is number 46 on our in-class assignment. We want to know what alkenes are formed when each alcohol is dehydrated with toluene sulfonic acid. We could have chosen sulfuric acid here. It doesn't necessarily have to be toluene sulfonic acid. Label the major products when a mixture results. So we just need to see what are the possible beta hydrogens that we could eliminate. We could eliminate a beta hydrogen on this carbon and one on this carbon. We'll go ahead and we'll start with this carbon. If we eliminate there, we will end up with this tetrasubstituted alkene. Clearly that one's going to be the major product. And then here, if we eliminate on this one, all right, then we would get that. And that one is di-substituted, so it will not be the major product. So we would predict this will be our major product. All right, on this one, we've got, let's see, we've got these two are identical. So we've got beta hydrogens here, and we've also got a beta hydrogen there. So let's do the one that's in the ring first. And we'll do that. So that would be one of our products. And this would be another one of our products where we eliminate there. Now, these are both tri-substituted alkenes, so they should be pretty close. However, if I were going to predict, and on this one I wouldn't expect you necessarily to predict, if I were going to predict, I would say that this one would probably our major product, and I'll put probably. And the reason for that is that when we have an option of forming an endocyclic alkene and an exocyclic alkene, the endocyclic alkene is going to be lower in energy and more likely to be formed. Now, there's a variety of reasons why that's true, but this one is endocyclic, and this one is exocyclic. All right, now let's look at this next one. Here, you'll notice that we don't have any beta hydrogens here because this is a quaternary carbon. There are 4 carbons attached, so there's nothing that we can eliminate there. So our only options are here and here. And so we'll start with the one, again, that is in the ring. All right, so that would be that. And then that would be the other option, the exocyclic. On this one, there's really not much doubt. Here we've got a tri-substituted alkene. This one is a di-substituted alkene. And so the tri-substituted alkene would definitely be our major product. Major, having trouble spelling major here. All right, so that would be our major product there. On this final one, we really only have one beta hydrogen that is possible, which is right here. So our product would be this. So that would be our product. And of course, because this one is a primary alcohol, when we eliminate with this one would have to go by an E2 mechanism. It would be much slower than these other ones, which were all tertiary, and they would go by an E1 mechanism. All right, so that's number 46. Let's look at number 50. All right, and here on number 50, what 3 alkenes are formed when this alcohol is treated with sulfuric acid? Well, let's redraw that alcohol. So 1, 2, 3, 4, 5 carbons and an OH on the second carbon. So 1, 2, 3, 4, 5, and an OH that is on that second carbon. And so there are 3 alkenes. Well, there's only 2 types of beta hydrogens that are here. And so we can eliminate here or here. So let's go ahead and do the obvious ones for that. So 1, 2, 3, 4, 5. If we eliminate between carbons 2 and 3, we could get this. 2, 3, 4, 5. And if we eliminate between carbons 2 and 1, we would get that. Now, as far as what the other product would be, if we eliminate between carbons 2 and 3, we can also get the cis isomer. 2, 3, 4, 5, and we would get that as our cis isomer. All right, and so of these, the one that is the lowest in energy, the one that would be the major product, would be this. That would be our major product, and that's because it is the trans isomer. This one is the cis isomer, and of course this one is just mono-substituted. So we've got di-substituted, but the trans will be greater than the cis, and then with the mono-substituted, we would have, that would be a minor product. Okay, so now we want to go back and look at carbocation rearrangements. So carbocation rearrangements. And this is kind of cool. This is, it's kind of fun. So sometimes we will get unexpected products when a reaction has a carbocation intermediate. That carbocation intermediate, the carbocation intermediate would rearrange. So something weird happens in the middle of the process. So if we look at this particular reaction, you'll notice the structure here. It has, we've got this quaternary carbon here that's got 4 carbons attached. So there's 2 methyls on carbon number 3 of this. But when we look at the products, we don't have any carbons that have 4 carbons attached. That means we must have had a rearrangement. Some of the atoms must have moved. So some of the atoms must have moved. The reason that this happens is we get a rearrangement while the carbocation is present. and that can cause a unexpected location for your carbon-carbon double bond, and also unexpected locations for some of your carbon atoms. So it causes a change in the backbone of your structure. So what is happening here is something that is called a carbocation 1,2 shift. And there are two types of 1,2 shift that we want to look at. So the carbocation rearrangements occur when a group, and it can be either an alkyl group or a hydrogen group, those are the two types, migrates from an adjacent carbon to the carbon with the carbocation. And so here is what it looks like. We've got a group, and again, it can be an alkyl group or it can be a hydrogen. And when it shifts, we're going to take the pair of electrons that is in that bond, and it's going to move to the atom with the carbocation. And so there we will get we get a 1,2 shift. Now it can only shift over one carbon. You can't just do magical shifting from the other side of the molecule. So it only shifts one. And the two types that we can have are a 1,2 hydride shift and a 1,2 alkyl shift. And like I said, either one of those can happen. Now, they don't happen just to happen, because there is a significant activation energy for this to occur. So in order for it to happen, there has to be a benefit to it. All right, so the driving force for this is the formation of a more stable carbocation. And down here, I've got an example of it. I'm going to go through each individual step. In step 1, we're going to protonate the oxygen to produce a good leaving group. So here we've got an alcohol. We protonate it with our sulfuric acid, and we will get this protonated alcohol. The second step is that we're going to get heterolysis, so we're going to break that bond. The oxygen is going to take its electrons with us, and that will give us water. And now we have a secondary carbocation. And then we're going to have a 1,2 shift of the methyl group. So this methyl, and it doesn't matter which methyl we pick, they're all identical. So one of these methyls is going to shift over to that where the carbocation is and make a new bond, and when it does, that there will no longer be a carbocation on that particular carbon, but there will be one on the carbon that we just left. Well, you'll notice that now it is a tertiary carbocation, and since tertiary carbocations are more stable than secondary carbocations, that is the driving force for this reaction. So almost always when we have a 1,2 shift, we're going to go from a secondary carbocation to a tertiary carbocation. There are occasions where it's not the case, and that happens when there are some other atoms attached, and we'll discuss those at a later point. But for now, we will just say typically it's a secondary carbocation going to a tertiary carbocation. The primary reason for this is that, one, we can't form primary carbocation, so we can't start there. And shifting from a secondary carbocation to another secondary carbocation doesn't give us enough energy benefit to overcome this activation barrier. So this is pretty much exclusively going to be something that happens when we can form that more stable tertiary carbocation. All right, once we've formed that carbocation, then the beta hydrogen is deprotonated using some base, usually just the conjugate base of our acid, comes along and deprotonates at a beta hydrogen. In this case, there are two different types of beta hydrogens. If we deprotonate there, we will get a tetrasubstituted alkene, tetrasubstituted alkene. And here, if we deprotonate there, we will get a disubstituted alkene. Of course, the tetrasubstituted alkene will be the major product in this case. As I mentioned a little bit earlier, it is possible for hydride shifts to occur. And the hydride shifts, when they occur, again, the driving force is going to be to shift from a secondary carbocation to a tertiary carbocation. We'll find that these rearrangements can occur in any time a carbocation is formed. So all of those carbocation reactions that we've looked at before, rearrangements can occur with those as well. If we've got a secondary carbocation here, if we just shift an alkyl, we will still have a secondary carbocation. But if we shift this hydrogen, the hydride, including its pair of electrons, we will form a tertiary carbocation. If we already have a tertiary carbocation, then we can't. Then we won't be able to do a shift. So there's no driving force for this to rearrange. So we want to look at number 57 on the in-class assignment, and this is a stepwise detailed mechanism with arrows. So it's a little bit of an involved reaction, and so we will do this one. Okay, so I'm going to start by redrawing this. All right, so here we've got our acid, sulfuric acid, and I'm going to draw the sulfuric acid this way, so HOSO3H. Sulfuric acid, just in case you're curious, don't know if I've drawn that before, but that's what sulfuric acid looks like, and here I'm just drawing a shorthand version for that. We're going to protonate that OH, so step 1, protonate. So we'll go from the lone pair of electrons to the hydrogen, from the pair of electrons in the bond to the oxygen, and that will give us OH2 plus. That will give us that. All right. In our next step, our water is going to be our leaving group. So we'll just take that bond and we'll go to the oxygen, and that will give us our carbocation. So we will get that carbocation. All right, and then plus H2O, of course. All right, and here it's beneficial to pay attention to which carbons are which. So I'm going to say here we've got carbon 1, 2, 3, 4, 5. We're going to call this one carbon 6 and carbon 7. And then this one I'll just call carbon 8. And this is just for labeling purposes so that we are able to identify which carbon is which and what is going to be bonded to what. You'll notice that we have a secondary carbocation. Over here we've got a quaternary carbocation. We could take carbon 8 and shift it over, and that would give us a tertiary carbocation, but that would still leave us with a 5-membered ring, and we wanted a 6-membered ring. So in order to do this, we either need to shift the bond between 1 and 5 or the bond between 1 and 2. Now, turns out those are identical, so it doesn't really matter which one we pick. Because it's easier to do, I'm going to pick the one between 1 and 5, and we will draw that bond to carbon number 6. When we do that, that will create a carbocation on carbon number 1. All right, and there is still a hydrogen that is on carbon number 6. So let me label these. So our carbocation is now carbon number 1, 2, 3, 4, 5. We broke the bond between carbon 1 and 5, and we now have a bond between carbons 5 and 6. So here is carbon 6. There's 7, and there is 8. And then we've got one last thing to do, which is we need to remove this hydrogen that is on carbon 6, and we're going to do that with the conjugate base of our acid that we started with. All right, so O, SO3H, negative, and we're going to deprotonate. So we'll draw a bond from that oxygen to the hydrogen, and then from this bond to that bond to make the double bond. And then up here, carbons 1, 2, 3, 4, 5, 6, 7, 8. And that keeps track of everything. We also here would have plus H2SO4. That means that the sulfuric acid is just a catalyst in this. So sulfuric acid here is a catalyst. All right, and before we end this video, we're going to go to the next section because it is also about dehydration. So we're going to switch over to we're going to talk about dehydration of alcohols with POCl3. So POCl3 is phosphorus oxychloride, and it is a good dehydrating agent, but it works differently than acids do. Instead of making the OH a better leaving group by protonating it, you make it a better leaving group by reacting it with the phosphorus, and then make a new leaving group that is just much better as a leaving group. Typically, you'll use pyridine as something to help the reaction along. So cyclohexanol, here's the POCl3. Pyridine is an organic base. I think we've seen this one before, but if not, there it is. And pyridine is good at removing hydrogens, and if we didn't, we would build up some acid in this reaction. So we need that base to finish it off. This is also an elimination reaction, so it's similar in that respect, that it's an elimination reaction. Let's look at the mechanism. I'm not going to make you reproduce this particular mechanism on the exam, but it is kind of an interesting mechanism. So the POCl3 makes the OH a better leaving group by reacting with it. There is a substitution reaction that occurs between the OH group and the POCl3. So we kick out the chloride, and we make this new leaving group. The pyridine comes along and deprotonates that, and when it deprotonates it, we can then create this. And this, like I said, is going to be a good leaving group. So ammonia will come in and deprotonate the beta carbon, form a pi bond between these two carbons, and then break the bond between carbon and oxygen. That leaves us with this new thing over here. So the POCl3 is used up in the course of this reaction. So you do need to use a stoichiometric quantity. I forgot to put these other steps here. But this is just another way of doing dehydration. All right. Again, I don't expect you to memorize this particular mechanism, but what is useful about this mechanism is, about understanding it, is that it is an elimination reaction, that we do create a good leaving group, and it does typically occur by an E2 mechanism. So we don't form a carbocation in the process of doing this. So very clean way to do it, and it makes it so that you don't have to use a strong acid that might mess up some other part of your molecule. All right, we're going to end this particular video here, and we'll pick up on the next by looking at how to convert alcohols into halides.